Hello, my name is Adrian and I'm going to be talking about algorithm analysis. So in this first video, I'm going to be talking about some basic definitions. Let's start with algorithms. So algorithms are a step-by-step instruction on how to solve a problem or accomplish a task. For instance, when you have a recipe you're doing to do a dish, you follow a series of steps on how to do it. That's an algorithm. Usually we refer to algorithm in terms of computer. We are going to focus on that from now on. Let's do an example. Let's say that we have an array of numbers, something like this. And we want to compute the sum of the total of the array. So we can represent the algorithm in different ways. One of them is using a flowchart. We're going to be using right now, just for simplicity, just to give you an example. So let's do that. So what do we have here? So we have a flowchart where we read the value of, we read n, and we will say is the input of the program, which is in this case is the array. We initialize our variables. In I, we're going to have each one of the indexes, 0, 1, 2, and s will be the total sum. So we are going to go through all the different numbers until we reach the total length, right? And for each number, we are going to add it to s and then increase the index. So we're going to start here. So this will be 0, this will be 1, this will be 2, right? So when we finish that, we just print the variable s and we're done. So not too hard. So now that we develop our algorithm, I'll give an example. We need a program to run the algorithm. So a program is an implementation of an algorithm. So let's say that we have a computer, right? And in this computer, we enter the algorithm, right? We're running the program. We type the numbers through the keyboard. We are going to get the result, which is in this case will be 2 plus 3 plus 1, which will be 6. So that's a program. So the program has an input, right? We have the program here. The program runs the algorithm, and then we have an output, right? If you notice, in the implementation that we did, we have used some variables and to store the input. Let's use another color. Let's use purple. I for storing the indexes, s, right? So all of these variables are data structures. So data structures are ways to organize data for later manipulation of algorithm or transform it into a totally different thing. So there are different types of data structures. We have arrays, we have variables, we have trees, right? We have graphs, and so on. So depending on the algorithm, we may use a different type of data structure. So that's data structure. So the last part we're going to be talking is about algorithmic problems. So algorithm problems is the process of finding the algorithm to solve a problem, right? So we have the input. We have to develop some algorithm, which we don't know. That's the problem, right? And we know the desired output. So the desired output could be a sorted number of arrays, or the total sum of the elements in array, whatever, right? So here comes algorithm, which will be run in a program, right? So for any algorithmic problem, there are multiple implementations of algorithm. You can have algorithm A, which solves the problem, but you can also have B, which gives the same output. However, they may be different. One of them may take certain time, and the other may take longer, right? Some of them also may have use different data structures. Some of them may use the same data structure given, the same array, but others may use more auxiliary data structures to hold data and transform it into different things. So we need to compare which algorithm is better. So we have two dimensions that we focus on: is time, how long it takes to run the algorithm, and space. So in the previous section, we discussed that when we have an algorithm problem, right, we may have different implementations to solve the same problem. So we may have algorithm A, may have algorithm B, and so on. There are actually infinite algorithms that can solve the same problem, but each one of these implementation may run at different times. So we want to know which one is the best. So how do we know that? One intuition could be to use a stopwatch, right? And we can time how long it takes to run. How long it takes to run the algorithm A, how long it takes to run algorithm B, and then whichever run less, we will say is better performant. But if you run it multiple times, you will notice that these values may differ, may be a little different, or sometimes they may win and the other may win the next time. So what happens is your computer is sharing the CPU with different processes, and sometimes it's hard to isolate your program and to benchmark it correctly, because there are many things competing. But also, if you run in your laptop and then you run it in a mobile device, it may take different time. Even the same algorithm may take different times. And if you run in your smartwatch, it will be even another different time. So depending on where you run it, if you run it in the cloud or a supercomputer, it's also different. So how do you compare algorithm that doesn't rely on the hardware is run, or what programs are you running? So if you run, let's say if you're playing Fortnite and you're trying to time benchmark, it's also going to affect the measurements, or running some heavy applications like Photoshop or some video editing. So how do we do that? So before we answer that question, let's step back and let's see the big picture, what we're trying to do here. So let's start with the algorithm. So let's say that we have like a flowchart to represent the algorithm, right? That's the idea, how to solve the problem, right? Which one of these implementations. So this algorithm gets converted into source code, which is written in a programming language. Each line of code or statement will represent an instruction, right? And then we have the program, which is the implementation of the algorithm, but this time in binary. So you have binary instructions. This is what the CPU can understand. So this program has the binary of SAS instructions, CPU instructions. And depending on the speed of your CPU, so the CPU internally has a clock that every time, so let's say this is a 1 gigahertz CPU, So every 1 nanosecond it will emit a pulse, and this pulse will take a piece of the program, some instructions, and execute one instruction at a time. This is 1 nanoseconds, maybe very fast, so it will distribute around all the programs in the operating system or everything running, and will take a piece of each one and will execute a little bit. So that's why you can measure programs reliable on this level, because it's being shared. CPU is being shared by a lot of different programs at the same time. So if we want to be hardware independent, we have to go up one level. We have to go to the source code. And this is what we're going to do. We're going to estimate how many computations each statement on the programming language, on the source code, how many computations we have to perform based on the input of the program. So let's do an example so we can drive this concept home. Let's say we want to write a program that finds the minimum element in an array. Let's do that. So let's say that we have this function, right? So we iterate through each element of the array, trying to find the minimum. And when we find the minimum, and then we are going to return minimum. That will be the output of the algorithm. So let's say that we have, let's do 2 examples. So let's remember that we want to estimate how many computations we have to do per each statement. So for instance, let's say that we have, let's use a different color. Say we have an array of two elements, right? So we have get minimum to 1, and then let's say we have an input of 4 elements. Let's say we have 3, 2, 4, 1. So let's see how this runs. So what we're going to do here is count how many computations we have to do. So let's say this one gets executed 1 time. So it's an initialization. So we have run this 1 time, right? And we assign 2 to minimum. And then we run this, the number of elements that we have in the array. So for each element, which will go to A, so we have 2, 1, minimum will be equal to 2, and then first element will be 2. So this line here gets executed 2 times, because we have 2 elements. And this if statement also gets executed 2 times because it's inside this. However, this condition inside the if statement doesn't execute all the time. So let's see how many times it gets executed in this particular case. So we have 2 is less than 2, no, so it doesn't get executed. And then we have 1 is less than 2, yes, so it got executed 1 time. And this return statement is also 1 time. What about this case? So this is an initialization, and then it gets executed 1 time. This for each will go through each one of the elements, which get executed 4 times, because we have 4 elements. And then we say 3 is less than 2, yes. So first the if statement will be executed 4 times as well, and this one is an easy one, will be executed 1 time, and this we don't know yet, so let's figure it out. So we have 3 is initialization, 3 is less than 2, yes. So 2 will be the minimum. So you can execute it one time. So then you do 2, so minimum is equal to 4 is not the minimum, then 1 is the minimum, so you get executed 2 times. Okay, so what do we have here? So if we do a generalization, we can see that this one is a constant. It doesn't vary. As the input grows from, it's always the same. So this is the same, and this is the same. We can say this is K1, this is a constant. K3, let's say this is a constant. And let's assume that this is a block that gets executed sometimes, so it's a constant too, right? So what do we have here? We have, let's call this block, yeah. So we have K1 plus, but this gets executed n times. See, if where is equal to 2, when it was equal to 4, it was executed 4 times, so we have 4 times K2 plus K1, K3, right? So we have some formula in here, and now we can estimate, oh sorry about that, to be n, so n times. So if we have an input of n equals 10, we know that this will be a constant, this will be a constant, and this K2, this block here, will be executed 10 times. So we have a pretty good estimation of what is going on. So this T here, so we call this time complexity. So the time complexity is how many instructions, how many computations are executed on terms of the input. So the input, in this case, is n, right? So we have n, oops, what is this? And then we have the input n, and then we can estimate how many computations will be performed. So as you can see, the time complexity will be given in function of the length of the input and also the arrangement of the input. So how do we prove that? So in this first case, let's do another example. In this first case, when we have 2 and 1, this line here executed 1 time. But let's say that we have the same, let's do another example. Let's say we have 2 and 1. Let's say we have 1 and 2. Let's find the minimum, this one. So the first one will execute 1 because this is a constant. This line will be executed n number of times, which will be 2, right? And this will be executed 2 times as well, because that's the length. However, this one in here, let's see how many times it's executed inside the minimum equal 8. So the minimum is 1, and then we are iterating through the array. So 1 is less than 1, no. Then we have the second element, which is 2. So we have 2 is less than 1, no. So this one got executed 0 times. That's interesting. So 0 is not the same as 1. Everything else will be the same. So you can see that the arrangement, even though it has the same length, it executed slightly more operations on this case than with this case, and both are n equals 2. So what do we learn from here? The arrangement of the input matters, and the length of the input matters. So depending on how the input is arranged, we have 3 different cases. So we have the worst case scenario, we have the best case, and we have the average case. So for the worst case in the get minimum program is when the numbers are in ascending order, it didn't execute any operation here because it will be initialized to the first one, which will be the minimum already. So it won't perform this line will never be called. However, when it's in different order, in descending order, then this line will always be called if all the numbers are. So we can say, so numbers in descending order are the worst case. We can say ascending order is the best case, and the average case will be random, where the numbers will be either ascending or descending, a mix of them, and then we don't know. So still, for this case, we have a time complexity of this function. So even if it's a worst case or best case, we still will be executing this part, this whole k2 n times, right? So the runtime for worst case will be m for each one of them. However, if there are some algorithms that the worst case may be a different time. Maybe the worst case will be n squared, the best case will be n, and the average case will be n squared. And this is for some sorting algorithms. But for our case, it will be just all n. So, just an example. Finally, the last concept that we want to bring is big O notation. So big O notation. So in this case, we got a time complexity of Cn. We have a couple of constants. Call it constant 1 and 2, then k3. So if we do a chart where this is the input size, and this is the time complexity, or the number of instructions executed, we will have something like this. We will have straight line. Depending on the constants, it will be more up and down, but it will be a straight line. That's what matters. So big O notation is a function that concerns with the worst case, right? So the worst case is when this line will be the highest towards, it will execute the most amount of instructions or computations. So the time complexity is a function, something like this, another function that will wrap this one. But it could also be like so this n is a linear function, and the time complexity could be something, whatever is higher than that. It could be n, or it could also be n squared, or whatever function is higher than that. So when we are doing the big O notation, usually we try to get the function that approximates like the closest to the function that we have. So in this case will be n, and we represent it as O n, this case, right? And this will be the big O notation of this time complexity. Another way to see it is that we are, as the n, what we care about the most is when the values of n start growing bigger. So in this case we have n of 2 and 4, but what about if it keeps growing? So n gets to 10, or gets to 100, or gets to 1 million, and so on, or even infinite. So when the n tends to the infinite, these values, these constants are less and less significant, and the one term that is going to matter the most will be the highest order term, which is, in this case, it will be n. So this kind of approximation is called asymptotic analysis. Right? So this asymptotic analysis we do is that we only care about the higher order terms, because when the algorithm start growing, the number of inputs in the algorithm start growing and growing. This is the value that's going to matter the most, and also it makes it more convenient to compare algorithms. So we could have algorithms that are n squared, then we know this one will execute a higher number of computations, so that's a worse algorithm than one that is n. So in the next video we're going to see an example of each one of the different big O notations, or the most common at least, and provide a code example for each one of them so you can drive this concept home. Thank you. Bye.